Swayam Prabha. Digital India. Educated India.
Welcome to you this course on fluid mechanics. It's very interestingly that today we have 10th lectures, which is the halfway of the fluid mechanics course what I've been teaching you, and today we'll cover the conservations of momentum and its applications, which is really an interesting subject in the fluid mechanics using the Reynolds transport theorems and the control volume concept. Considering that aspect, I will go through you how we can simplify these Reynolds transport theorems for control volumes, and how you can simplify in terms of pressure distributions and the velocity distributions. So, how we do the simplifications of these equations, and then we apply that equations for engineering applications like finding out the force components, the velocity component and the pressure distributions. As I said it earlier, I just follow the books of these three. Mostly I am talking about a mid path between fluid mechanics books by F.M. White, which is bit mathematical oriented, whereas if you talk about fluid mechanics fundamental and applications, which is more illustrative oriented. So, I try to make it you in between of these mathematics and the illustrations oriented, and other book as you know it, this fluid mechanics by Professor Vidyasagar Pani. So, let us come back to the recap of the previous lectures. As you said it earlier, basically the mass conservation equations, and we also solved the gate questions on mass conservation equation. Then we also discussed very details that the Reynolds transport theorems for linear momentum equations, and that what for the two control volumes, one is fixed control volume and another is moving control volume. And that what we talk about the force acting on a control volume. There will be two type of forces, body forces and the surface forces. The surface forces are pressures and the reaction forces, that what we will talk a lot, discuss also today. Body forces, mostly what the problems we can consider is only the gravity force we consider as a body force, not the electromagnetic forces. Then we also discuss about the momentum flux correction factors, is a very simplified concept used to determine the momentum flux passing through a non-uniform cross sections, and using this correction factor, momentum flux correction factors. And also I gave you a example of jet experiments, how we conducted in laboratory. Now let us come to today's lectures. We will have a steady flow approximations for the linear momentum equations. Many of the times we have a linear momentum equations we solve for the one inlet or one outlet and in one directions, and some of the problems we have to solve with no external forces. Then how the momentum equations can be simplified it. Then fourth, what we will talk about, when you apply the linear momentum equations, what are the hints and the tips, what should we consider when you apply the linear momentum equations. Then I will commit to solve 4 example problems of previous gate questions, we will solve it, then we will have a summary of today lectures. Now let us come back to very interesting 3D figures, what you can see it. It is there are bridge piers, the bridge piers are here, and the flow is coming it, which is unsteady flow. And if you look at this color fringes, it is showing it how the pressure diagrams are changing. Just you look at how the 3D view we are getting it, how the flow is passing through a bridge piers and how the pressure distributions are changing it. If you look at these colors of these ones, how the pressure distributions are changing it. This is today's world is possible because the computational fluid dynamic solutions are available as well as the 3D visualization tools are available. So, you can feel like that we have conducted an experiment in a flume to get it how the pressure distributions, how the flow depth variations is happening it in a group of bridge piers are there and how they are interacting each other. So, if you can look at these 3D figures. If you look at this way, this flow is unsteady, it varies with the time, incompressible flow, 3-dimensional and the turbulent flow. So, all complex flow we can solve it using the CFD and we can visualize that flow in 3D visualization. Somebody can feel it, how the flow is going on. If you can look at that, there is a breaking of the waves is also happening it. If you just look at there is a breaking of the waves are happening it and how this flow is coming it, how the heating in different bridge piers and the different bridge piers having the different amount of pressures acting on that. The force due to the pressure diagrams are the different. So, these type of visualizations nowadays it is possible with help of the CFD solutions and the 3D visualizations. It is possible nowadays to solve the full phase turbulent Navier-Stokes equations with some approximations. It is possible. So, that is my point to tell that even if I just talk about the control volume concept which is a very gross characteristics, but today it is possible to have these two 3D visualizations and the CFD solutions which gives us just a real life problems like what I am showing it, a pre-surface flow around a bridge, the breaking of the waves and also the pressure distributions are changes from the pier to pier, all it is possible because of the CFD solutions of 3-dimensional turbulent unsteady incompressible flow. That is what is available, also 3D visualizations. With this note, let us go to the our level where we are talking about the integral concept of control volumes, what we apply it for a simple problems. Now, go for a simple problems where you have a linear momentum equations like you have a fixed control volume. Just to look at it, you have a fixed control volume. There are the in are there, okay, and there are the outs are there, and this is the fixed control volume. So, there is a influx, this is the outflows, there is influx and outflows. The sum of the force will be act on this if it is a steady linear momentum equations. The time derivative components becomes 0. So, we will have a sum of the force is equal to, this is still I am putting in a vector notations, is equal to the, in case of steady, the difference between the rate of outgoing and incoming momentum fluxes. So, what we will do it, sum of the momentum flux what is coming as a inflow, that means the mass flux into the velocity, that is the momentum flux. Then we have the beta 1, beta 2 which is representing momentum flux correction factors which will differ from the 1 to 2, 3, 4, 5 locations because the velocity distributions are the different. So, as the velocity differences are there, so you will have a B1, B2, B3, B5 will be the different because the momentum flux correction factors it depends upon the velocity distribution. If when you have velocity distribution uniform, the beta 1 will be the 1, but if it is not uniform, the beta 1 value will be the different. So, the basically if you look it to apply this concept, we use the velocity distribution as a, considering the velocity distribution we consider momentum flux correction factors, we have mass rate into the velocity which is the momentum flux rate, that what we are summing it how much in and how much going out from this, incoming momentum flux and outgoing momentum flux. As you know from vectorically, so outgoing momentum flux will be the positive and incoming momentum flux will be the negative. So, the rate of change of this net outflux of this momentum flux will be the force component. The sum of the force component over this control volume, that what will be the net outflux of momentum fluxes through this control surface. So, in this case we have 3 outlets, 2 inlets. So, for the 2 inlets we can compute the momentum flux from 1 to similar way we can compute the momentum flux which is going out 3, 4, 5, we can compute it. Also we can consider the momentum flux correction factors which will be the different for the different inflow or outflow flow distributions, velocity distributions concern. So, we have considered that fact that there is a velocity distributions variability is there, mass flux in and out different will be there. So, considering this, in this control volume, fixed control volume, what will be the net force which will acting on this will be considered as a steady problems, then you will have these conditions. Okay. You can easily find out if it is a steady problems, you will have a definitely the net mass influx in should equal to the net mass influx going out from this, that should be equal. So, whatever the sum of the mass influx is coming it, that should be equal to sum of the mass outflux is going out from this control volume. Then we have the steady problems. So, this is the conservation of mass equations and this is the linear momentum equations for the steady flow having multiple inlet and the outlet. Now, let us go for another simplifications, that in a steady flow conditions, okay, and only one outlet, one inlet. This is a very simplified case. See, when you have a one inlet and one outlet, if your mass influx is m dot 1 is a inflow is coming into that, your mass influx out will m2 dash, that should be equal. That means, rho q1 rho q2 will is equal, that means q1 equal to q2. That is a very basic equations what we get it if we apply the conservations of mass. So, if a mass influx what is coming in that is equal to mass outflux, that what we can designate as a mass influx rate m dash, then the sum of the force acting on this as a steady conditions, what will happen it, that sum of force equal to the mass will come out B2 V2 minus B1 P1. So, outlet inlet momentum flux what we are getting it with a correction factors of beta 1 and beta 2, we have used it to compute the momentum flux what is coming into the control volume, what is going out from this control. The net momentum flux, that what will be the force component, that is the equations what you get. So, these simplifications what we are doing it, that sometimes you can directly use it these equations instead of to use of Reynolds transport theorems, then you simplify it, then you come it. Instead of that, if you have solving a steady flow problems with one inlet and one outlet, to find out what is the force is acting in that, you can directly substitute these equations as a linear momentum equations, and these equations you can use as mass conservation equations, which is q1 equal to the q2. That is very simple way we can do it. Now, there are the problems where is come it very interestingly that we can apply the momentum equations. As you can know it, this momentum equations is a vector equations. It has a 3 components of in scalar directions, s component, y component, z component. Many of the time we result a specific directions, in this case is x directions, to find out the force components. That is what we try to look at, what will be the force is happening it in the x directions only. So, we can use it only the x direction component part. Since there is these problems, if you take it, there is a water jet is coming it and going out, there is a change in the directions of the water jet, okay. And there is a support system for that. What will be the force acting on this? That is what the problems. That means, there is a water jet is coming which is making an angle theta, then making a turn it, that becomes a horizontal water jet. So, because of the change of the momentum flux directions, what is the amount of force is acting on that? If I am resolved it only this x directions component, then what I will do it, I will find out the momentum flux in x directions only, not the y or z direction, because I can have a 3 equations. Here we have a very good simplifications that if I am to compute the force component only the x directions, if I consider the control volume this like this, I know it, the force, the gravity force act in the z directions. So, that force component will not commit. So, this is what quite simplifications we are supposed to do it when you consider only the x direction, the force component of x directions. You know it, the force acting on the either in y or the z direction, that may not have any components. So, that way you can result the force component as a scalar component only x directions. So, you compute the momentum flux what coming in the x direction momentum flux. Similar way, what is the momentum flux outgoing, that what we compute it. Sometimes you can exactly a vector method we can flow it if you do a vectorically, the momentum flux in and the out, that can vectorical, that what is the momentum flux is a force component. So, you can resolve this force component and the resultant force you can get it. That is what we can simplify, you can solve this directly, that these are the momentum flux as equivalent to force what is coming into this control volume, going out from this control volume. You know these two forces balance with a resultant forces, that what vectorically you can find out what will be the FR value, that what will be the reaction forces. So, this way we can also simplify either considering this control volume or writing the force vectors due to the momentum flux in and out. From there we can get the resultant force components and we can get it the what is the reaction force component. So, we noted that V2 should not equal to V1 if it is that. Okay. So, that because net force will be the 0. So, okay, there is no change in the velocity directions or the magnitudes, then there is no force which is going to act on this. Now, if you look at there another set of the problems we solve it where there is no external forces is there, there is no external forces is there, very simplified cases. So, in that case if I use the linear momentum equations, the sum of the force will be the 0. So, what will happen is that rate of change of momentum on a control volume, that is what is here, that is equal to the difference between the rate of the incoming and outgoing momentum flux rates in absence of external forces. If there is a, you consider a control volumes where you visualize or conceptually that there is no external force is acting it. So, that problem is quite simplified, because if you apply the linear momentum equations, the net force is equal to the 0. So, 0 what we have applied it. So, problems becomes rate of change of momentum within the control volume is equal to the difference between the rate of incoming outgoing momentum flux in absence of external. So, we have these 3 components with this. If you can simplify it is a momentum rate what is changes is that what will be the as equivalent is mass of control volume and the accelerations component. It is just like a rigid body is moving it. Okay. So, that what will be the force is moving it md, that what will be is that force will be equate with the difference between the momentum flux in and the out, that the conditions will come it, the momentum flux in and out will be there. The sign conventions if you look it when you have a positive and negative, just have the difference equations of we are equating it. So, you can find out in a systems the net fluxes of momentum fluxes what is going on in and out, that what will be mass of body is m body and has accelerations, that what will be equated to that. If there is no external force acting on that, or net thrusting force will be fixed mass body will be that much. Okay. This mostly we use it these equations for when you are launching the rockets, the net momentum flux what will equate it, the accelerated to the body, that the problems we solve it. I will solve one of the problems based on this concept. Now, comes back to the what are the tips are there when you apply the linear momentum equation. First thing is that do remember is momentum equations is a vector equations. It has a 3 scalar components. It has the directions. You can write it in x directions equations, y directions equations and the z direction equations. You can write it in the 3 directions. So, many of the times you do not result into 3 directions, we resolve the equations only one direction to solve a particular problems. Okay. But we can resolve these momentum relations in 3 directions x, y, z. So, when you solve these any linear momentum equations, please sketch the vector components. Then you visualize the fluid flow problems and then you solve it, because it is a vector equations, you try to apply as a vector equations. Second is that we always compute the momentum flux terms, influx and outflux direction. You always look at what is the velocity directions, whether it is a inflow or the outflow. What will be the conditions when you have a dot product or the scalar product of the velocity and normal to the control surface, whether it will be a positive sign or the negative sign. That what always you visualize or always try to draw the velocity diagram first. Then you have a control surface, you try to find out if I multiply the scalar product of velocity and the normal vector to the surface, whether it will be the positive sign or the negative sign. That means, if theta equal to 0 between the velocity vectors and the normal vectors, then we have the cos theta equal to the 1. Okay. Or if you have a theta equal to the pi degree, the cos phi will be the minus 1. So, that what you try to look at, that what is the directions of velocity vectors, what is the directions of the normal vectors to the control surface. If I do scalar product of the velocity and the normal vectors, what is the sign, with either positive or negative sign. Many of the time the student do these mistakes, that they have a confused that whether you have to use a positive or negative sign. Please try to understand it, you are making a scalar product of velocity vectors and the normal vectors. So, if you know what is the angle between these two, if theta equal to 0 or theta equal to pi, you can find out whether it is a positive or the negative. This is very simple thing, but you sketch the velocity vectors, sketch the normal vectors, then you apply that. And one of the things what we always discuss is that whenever you take a problems, the velocity distributions is not uniform. Any real life problems, velocity distributions is not uniform, but we simplified it or make use of momentum flux correction factor, which considered the, because of non-uniform velocity distributions, what could be the correction factor to compute momentum flux through a control surface. So, that way we always try to look at that there is always a momentum flux correction factor will be there if there is a velocity distributions is not uniform. For a real life problems, velocity distribution cannot be uniform, and that is the conditions we always have the beta value or momentum flow correction factors. So, in a problems, if the momentum flux correction factor is not given it, you can assume it or highlight it that what you have done it, that you have assumed it that momentum correction flow correction factor is 1 or unit value. That is what you have to consider. It is very important things about momentum flux correction factors, and students should visualize that there is a flow distribution, the velocity distributions, that what is considered when you use the momentum flux correction factors. And second things what is there, the applied force acting all the material in the control volume, we do not bother about inside the control volume, how the non-control surface, the force acting part, that what self cancelling each others, that what we do not consider it. We talk about over the control surface, what are the force is acting it, that what we consider it. And the last one is what is that the fluid when it exists subsonically, that means flow is subsonic, flow Mach number is less than 1. In that case, if you flow exits into a atmospheric conditions, you can always consider the fluid pressure is atmospheric pressures. These are well known assumptions what we do it, and it's quite valid, that whenever the fluid exits subsonically, that means the flow is subsonic levels, that means the flow Mach number is less than 1 to an atmospheric, at that point we can assume it the pressure is equal to the atmospheric pressure. The pressure is equal to the atmospheric pressures. Similar way, as I said it earlier also, you always choose the inlet outlet which will be normal to the flow conditions. That is what I said it earlier. The scalar product between the velocity vector and normal vector to the control surface, that should have a either theta equal to 0 or theta equal to pi. So, it is very simple phi, we can solve the problems. Otherwise, it can be done it with a scalar product of these two vectors. It is not that difficult, but it is a laborious. Maybe you need a more time to solve the problem as compared to if you take a appropriate control volumes on the control surface, then you can solve the problem easily. Let me repeat these things what I have talked to you, which is very important when you apply the linear momentum equations, is that the linear momentum equations what we get it is a vector equations. It has a 3 scalar components, x directions, y directions and z direction. Many of the times when you solve a problems, you just apply only one momentum equations in one direction. You neglect other directions or that direction not necessary. But be remember the momentum equations is a vector equations, it has a 3 scalar directions equations, we can write it. Second things which is again I am to repeat it, that always you do not confuse on the sign convention. What time the momentum flux will be positive or the momentum flux will be the negative. Just look at that what will be the scalar product of the velocity vectors and the normal to the control surface. Is it theta equal to 0 or the theta equal to pi? That way it will be define you that whether it will be positive value or the negative value. So, do not confuse that why this sometimes we consider momentum flux is positive, sometimes momentum flux is negative. So, this because of the scalar product, the sign of the scalar products what we have considered it between velocity and the normal vector to the control surface. The fourth one what again I have to repeat it, any real life problems the velocity distribution is not uniform. There is always a velocity distribution as there from the free surface to the surface of contact, that there will be a velocity distribution. What we do it, we do not consider, always you consider, do not consider integrations of that, instead of that we consider distributions of velocities, compute the momentum flux correction factors for that type of flow velocity distributions, and that correction factor we use and the average velocity to compute momentum flux. So, momentum flux correction factor and average velocity we have used to compute momentum flux what is going through a control surface where you have the velocity distribution is not uniform. If you uniform it, velocity is the same throughout this control surface, beta becomes 1 value. And last 2 points what I am to talk is that many of the cases what we have considered this flow exits into the atmospheric at the subsonic flow levels. That means flow Mach number is less than 1. In that case, you can consider the pressure is equal to the atmospheric. And the last point already I discussed is that we always choose the control surface such a way that it should have a normal vector and the velocity vector should be having an angle of theta equal to 0 or theta equal to pi. That is the main tips what we need to do it before applying the linear momentum equations. Be remember it, it is very easy to solve any complex problems if you appropriate linear control volume you consider and you have a assumptions and all things you clearly note it. looking that, I know the problems what I am going to solve with these 4 examples can be solved directly putting the momentum equations, but I do not follow that. I follow very systematically the first flow classifications, second I do appropriate control volume, sketch pressure diagram, force diagrams, then velocity diagrams, then apply the continuity equations. Finally, I use the momentum equations. So, if you look at that, whenever you get a problems, do not be excited that to apply the linear momentum equation as of you got the equations, simplify equations. Instead of that, please follow these procedures. That first you do a classification of fluid flow problem, what type of problems you have. Second, you try to sketch the control volumes, which is appropriate control volumes and the control surface. Third, you look at what could be the pressure distributions. Fourth, what could be the velocity distributions or momentum flux correction factors. Then you go for applying the mass conservation equation and linear momentum equations. Please follow these procedures. Then if you follow these procedures, I think doing the error during the solving the problems, that what will be nullified. Otherwise, if you apply the linear momentum equations without a proper control volume, it is expected that you will do a mistakes as compared to if you follow appropriate control volume, all the assumptions are clearly highlighted, then you can solve the problems, and that what will have a chance to do the error will be nullified as compared to solve directly using linear momentums. To demonstrate that, I am just going to solve these 4 problems, and you look at how I am doing the assumptions one by one. Then I am applying the mass conservation equations and the linear momentum equations, not directly applying the mass conservations or linear momentum equations. Yes, so let us solve 4 examples considering the concept what I said earlier. First examples I have taken it that a linear flow is passing through very long straight round pipe with axial velocity components. So, velocity component is given it, how it varies it. Okay. This is the pipe. Okay. So, if r is a radius of inner wall of the pipe, V average is the average velocity, then calculate the momentum flux correction factors. This is very simple problems. If you look at, you first draw the sketch. The sketch says that you have the pipe, okay, and there is a velocity distribution which is equal to r squares. So, that way the velocity is maximum at this point, r, capital R, that what will be the velocity becomes 0. So, that way you will have the velocity distributions what you will approximately will plot it, okay, what could be the velocity distributions, and somewhere this average velocity will come it like this. Okay. So, this is the velocity distributions, the laminar flow through a long straight pipe, this is the tentative velocity distributions. Now, we want to compute it, what could be the momentum flux correction factor if this is the velocity distribution. Now, let us classify the problems. Is it one dimensional flow because we are considering the velocity distribution, steady, laminar, incompressible. First you classify the flow. That is what shows that how you have done the assumptions to solve these problems. So, first you have to classify the problems. In this case, is a one dimensional flow I have considered because I know the velocity distributions. No doubt there is no time component is there. So, it is steady flow, flow is laminar is already highlighted, and we can assume it. In this case, the pipe flow may not have the Mach number more than 0.3, the flow can be considered as incompressible flow. Here, okay, we will not consider this control volume, okay, we can consider as a control volume and slicing the pipe normal, just you consider a control volume where you just want to make it what will be the velocity distributions. Now, we have these distributions like this, And since I have the average velocity V average at a sections and the velocity V vary from wall to the centers as given in these figures, then I am to compute the momentum flux correction factors. What is that? We need to compute the momentum flux. If I consider the velocity distributions, divide by the momentum flux. If I consider V equal to V average, the ratio between these two terms will give me the momentum flux correction factors, if you remember the definitions. So, if you apply it, what is the momentum flux? Rho A V square or rho Q V. Rho Q is my mass flux, V is the velocity. Mass into velocity is the momentum flux. Rho Q V or rho A V square is a momentum flux. Now, if rho is a constant, does not vary it, so it will be cancelled out it, then you will be V square by V average square by the DAC. So, please remember it, it is a very simple concept, is that the momentum flux what? Rho Q V, and if I substitute Q equal to A V, then rho A V square. So, first I am computing this momentum flux in terms of rho V squares to compute throughout these controls the surface rho A V square in DC by the average conditions what I am doing it, to compute what will be the beta factors. What will be the beta factors? So, I will take it a small element area at the r distance. I will take a small element here which will be the dr, in the radial direction, so will be the dr, and I will compute the area, I will substitute the velocity distributions, and doing these integrations I will compute the beta value. That is the point what will do it. So, if I have consider element area dr, the area will be the circumference into the dr, that what will be the area, length into dr will be the area part, and once I know this area and once I apply these things to the momentum flux correction factor equations, I will have a this form. So, AC equal to pi r squares, and I put the velocity distributions equations here, and we will 2 pi r and dr values we have. And once we have this part, and you just look at this V average are cancelled out, we have these functions what is there, okay, 1 by r square to the square of this, we apply the DAC values like this and the beta value of this. To do these integrations, we can consider y equal to 1 by r small r square by the capital R square, and in terms of y we are writing it to just do the integrations, nothing else. In that, if you look at when you have a r equal to 0, that means at the centers you will have a y equal to the 1 values, as equations implies to us. When you have r equal to r, y equal to 0. So, we will change this upper limit and lower limit of the equations when we are converting from dr to the y integrations. So, this is what 0 to 1, the minus 1 components are there, minus y square will be there, and if you substitute these values, and you will get it 1 by third. So, in laminar flow case, whatever the flow, these velocity distributions, the beta factor is called, comes to what 1 by third. That means, if you computing the momentum flux using these average velocities, the actual momentum flux going through that surface, if follow these velocity distributions, will be the 1/3 of that. If you look at that, if you have beta is equal to 1 by 3, what it indicates that the momentum flux using velocity distributions divide by the momentum flux using average velocity. So, what it indicates that the momentum flux using the velocity distribution will be the 1/3 of the momentum flux using average velocity. So, momentum velocity using the average velocity is much larger, and that what is to be divided by 1/3 to compute it the momentum flux using the velocity distribution. So, you can know it is what is importance of the momentum flux correction factors when the velocity distribution is not uniform. But of some of the cases velocity distributions, like for example for turbulent flow, this value is close to 1.01 or 1.04. So, for the turbulent flow. So, in that case you may assume it beta equal to the 1. But in case of the laminar flow and all, where you have the momentum flux correction factors are the different, it depends upon the velocity distributions, what type of velocity distributions you have. Now, let us come to the second example, which is very interesting examples, which is almost all the fluid mechanics book have these examples with some numerical values are the difference. The problem is very interesting problems is that there is a gate and the flow is coming from these sides and going out through this gate here. The velocity is V1 and V2 and H1 and H2 is the flow depth. This is the sluice gate. What could be the force, the horizontal force acting on this gate? So, that much of force necessary to hold it. Okay. What will be the final formula in terms of V1, V2 or eliminating the V2? If there is this numerical value is there, that upstream flow depth is 10 meters, H2 is 3 meters, V1 equal to the 1.5 meter per seconds and the density of water is 1000 kg per meter cube, then what will be the force? So, first what we will do it, we will solve the problems, we will write these final expressions, then we will substitute the value. As I said it earlier, we will follow the control volume concept. The first we have to have a flow classifications. What type of flow it is? One dimensional flow. We do not look at the flow in other components, we consider is one dimensional flow. Steady problems, whatever inflow is coming, that is what the outflow. There is change of the storage within this control volumes or this surface or not changing it, flow is turbulent and the incompressible flow. Now, we have to use a fixed control volume, that is what is there. So, we will use a fixed control volume. Now, if you look at in this control volume, we will apply the pressure diagrams, force components, then we will have some assumptions to nullify some force component, then we will apply the mass conservations and momentum, linear momentum equations. Now, first is the pressure distribution. Now, if this is my control volume, first I need to draw the streamlines. So, as it expected that the streamlines will be like this. So, as a virtual fluid bulbs, if you have, it could be like this. If the follow of virtual fluid bulb, if I follow it, it could be like this. So, we should consider the control volume such a way that at a so far distance such a way that all the streamlines should be the parallel. Okay? There is no curvature of the streamlines where we have the control surface is cutting over that. If that is the conditions, if streamlines are parallel, then the pressure distributions over this area can be considered as a hydrostatic pressure distribution. That means, as if flow is a rest conditions, whatever the pressure distribution, that is the pressure distribution will happen when the streamlines are parallel. That means, you define the control surface such a way that you can anticipate it in that region the streamlines are the parallel. The similar way at this outlet also we can consider it the streamlines are the parallel and I can consider the hydrostatic pressure distribution. Over this surface we always can consider the pressure distributions equal to the atmospheric pressures. So, we will use a gauge pressure concept to solve the problems. So, we need not to consider this atmospheric pressure distributions to compute the force. So, we can nullify that component. Second things, this is what the pressure distributions. Now, you have to look the velocity distributions. As you expected that here this velocity distributions will not be uniform. Okay. The velocity distributions will be there, the zero velocity distributions at the wall and this spherical gate. So, in this case we consider is average velocity, okay. We do not consider the velocity distributions, okay. Or we consider is beta is equal to the 1, the uniform velocity, but these are the assumptions which is not valid in a real life problems, okay. The velocity distributions will come like this. So, you have a uniform velocity distributions, what is assumption is there and make it a beta equal to the 1 value. Okay. So, this average velocity distributions are used it, and second thing that at this wall surface, the surface which is connected to the wall, definitely there will be a shear stress acting on this. Because of this shear stress there will be a force, but since here the force due to the pressure distributions and the momentum flux, rate of change of the momentum flux, those forces are much higher order than force due to the shear stress. So, we can neglect it as compared to the pressure and momentum force component. So, please remember it, there is a shear force acting on the bed, but in these problems, because the problem where you have these force components of F, the force due to the hydrostatic pressure distributions, the force due to the change of the momentum flux are much higher order compared to the force due to the shear stress at the bottom level. So, not to complicate the problems, we neglect it or we consider the force due to the shear stress is negligible as compared to the pressure and momentum force component. These are clear cut assumptions for velocity distributions and weight shear stress. Now, if you look it, as I said it is considered there is no velocity distributions, momentum is uniform, inlet, outlet considered. These are all assumptions is there. Now, I will apply mass conservation equations because it is single inlet and outlet conditions. The mass influx is equal to mass outflux is a very simple problems, m dash in m dash out, that is rho q1 equal to rho q2. Okay, this very rho cancelled out, q1 is equal to the q2. This is a very simple things what you applied, and rho is equal to this area into the velocity, that is what is average velocity v1 v2, and based on that you can compute what will be the jet velocity at this point. So, you know h1, h2, you can consider a unit width perpendicular to this surface, then the b will be cancelled out, or you can consider b width, then you can compute the what will be the velocity. So, if I substitute h1 equal to 10 meters, h2 is 3 meters, the average velocity what is coming 1.5 meters, as with depth of the flow is reduces, velocity increases. That the very basic conservation of mass talk about that. So, as the flow area decreases, the velocity increases. That the basic idea what it happens is as a proportionality quantity, it happens 5 meter per second in this case. Now, if you look it, I will apply the conservations of momentum. Here I am not simplifying the Reynolds transport theorem step by step. So, sum of the force acting on this will be rate of the change of the momentum flux storage within the control volume, net outflux of the momentum flux out in, that what will be there considering this beta values. So, in case of the steady flow, I can make it that is 0 and beta equal to the 1, that is what we have discussed it. And if I applying the force components only in these directions, okay, not in the x directions, my body force is acting on the y directions or the z directions. So, I will have a force get is equal to, this is the pressure force component at these locations equal to rate of change of the momentum flux. The mass flux will be the same V 2 minus V 1. That what will be the rate of change of momentum flux, and if I substitute it and solve with these equations, I will get it like this, very simple way. This is what the expressions will come it in terms of H 1 and H 2 V 1 and the densities rho. Then I will substitute the values as it is given here V 1, V 2, then I will get it. The force acting will, this will be 393.9 kilonewton per meter. So, this much of force will be acted because of the flow what is coming it, what is the change rate of change of momentum flux and the pressure force difference, that what will be exit will be force on the gate, that what will be get it from this case. Now, let us consider another problem which is a GATE 2007 civil engineering course problems. Is very simple problems. There is a horizontal water jet with a velocity 10 meter per second, cross sectional area is 10 millimeter square, strike in a flat plate held normal to the flow direction. What is the total force acting on a plate? That what is the questions. If you look at that, again we have to do flow classification. As is expected, as you see these diagrams, flow has two directions, okay, two dimensional. The force, the jet force what is coming in x directions, after heating it is moving the y directions, splitting into two part, moving in the y directions. If it is having symmetrical water jet, that is same amount of water will go in this direction and this direction, because the gravity force will have a much lesser component as compared to the rate of change of momentum flux, the force component much larger than gravity force. There will not be imbalance between these two velocity components. So, more or less the same amount of the flow will go from these directions and these directions. So, that way this water jet is doing that. We can consider a fixed control volume. Once you consider the fixed control volumes like this, then you apply the pressure distributions. If you remember it, that since these water jets are into the atmospheres, always you can use the pressure distributions is atmospheric pressure. So, over this control surface, I can find out the atmospheric control surface. Okay. Only the force what will be impact on this, what you need to compute it. Here also we have considered there will be a velocity distributions of the water jet, but we consider the velocity distributions is uniform, that means beta is equal to the 1. Assuming that we apply this momentum conservation equations, okay, and it is a very simple things. Momentum in flux will be momentum out flux, and if I apply it again this Reynolds transport theorems as basic equations, sum of the force acting on this control volume, that will be rate of change of the momentum flux storage within the control volume or net outflux of the momentum flux passing through this control surface. That what if I put it and take these assumptions or steady problems and flow is impacting in the x and y directions, and if I result the velocity components in a 3 component is 1, 2 and the jet, it will be the jet directions and these. So, some of the force acting on this will be the momentum flux x directions which is exiting from this, momentum flux these directions exiting out, and what is the momentum flux coming into this one. But as you remember, these two velocity component of this are the 0. So, only these components will be there, that what is the momentum flux V z rho v square a z. That is a very simple forward things, but we follow systematic approach to compute force on the plate will be rho v square A z. Substituting these values, we will get it 1 Newton value. Similar way, the same problems get 2012, only these additional things added to here. Okay. The same jet is there, but there is a horizontal nozzles 30-meter diameters discharge steady jet into the atmospheric at the rate of 15 liters per second. The diameters of inlet to the nozzles is 100 millimeters. Okay. That is what the 100 millimeters to the 30 millimeters. The jet impinges on a normal to a flat stationary plate held close to the nozzles and regulating air frictions considering the density of water is equal to 1000 kg per meter cube. What could be the force exerting jet on the plate is? This problem exactly the problems of the example 3, only these components are there. There is a one nozzles is there, which is having the reducing the diameters from 100 millimeter to 300 millimeters. Because of that, there is a change of the velocities, and that velocity impinges here to find out what is a force acting on this. The problem is exact similar problems what we discussed in example 3, only there is a nozzles is there. So, again the flow classification is two-dimensional, steady flow, turbulent and incompressibles, fixed control volume, and we will have a pressure distributions. We will consider all these atmospheric pressures. Average velocity concept we will use it. As you see, this velocity distribution will become it like this, not the average velocities or the uniform velocities, but to solve these problems we consider is average velocity and beta correction factors equal to the 1. And if it is that, now I apply mass conservation equations. First at the nozzles levels, inflow and is equal to the outflow, that is what is A in V in, the product of A and V in equal A out V out. Based on that, the velocity of the flow is going out from these nozzles. This part will be the same area proportionality to commit, which will be here 22.22 in K meter per second. This is V out from that, because as reduce the diameter of the nozzles, you will have more the velocities. That is the concept what is there. And now you apply the momentum equations. Momentum conservation equation we can also apply it for these control volumes. Another control volume we have considered when a jet of impact is loading it. Then we write the Reynolds transport theorems here, force is equal to these components. Then we simplified, this becomes because a 0, because of steady flow beta is equal to the 1, and again having the same component of x direction force component if you are talking about, which is you are computing what is the force is acting on that what will commit this value rho v square A z, V is already we know it, A z the area of the jet, and that what will force on the plate which will acting opposite direction of water jet, and that force will be the 318 approximately Newton, that much of force acting it. So, this way we have solved the 4 problems. Let me summarize the problems that we discuss how we can simplify the linear momentum equations for one inlet, one outlet combination. Momentum equations we can apply for a specific direction instead of vector equations, we can do it. We also discussed that linear momentum equations we can apply where no external forces exist, so we can do it. Then I discussed very thoroughly, whenever you draw the control volumes and try to find out the momentum flux, you follow certain hints and tips. And if you follow the hints and tips, you can simplify a complex problems and you can apply appropriate control volumes. Applications of the appropriate control volume is art, like a free body diagrams you apply for solid mechanics. Similar way, you should have solved the many problems using the control volume concept. As soon as you see a problems, you do a flow classifications and find out appropriate control volumes. And those control volumes, the surfaces and all should follow the hints and tips what we discuss in linear momentum equations. No doubt we discuss about 4 different type of problems to how we can apply linear momentum equations and the mass conservation equations. The next class also will discuss more example problems on these with a moving control volumes concept also. With this, let us conclude this class. Thank you.